Hello, everyone, and thank you for coming to our talk about lessons from long running investigations. We are Hossein Lotfi and Jana Iyengar. Let me introduce us before I get into the stuff of the talk. Let me introduce us briefly. Hossein is our VP of Engineering Network Systems. You will see him shortly, and he will give you a slightly more detailed introduction for himself. I am Jana Iyengar. I am VP of Product for Infrastructure Services at Fastly, and I'm responsible for Fastly's infrastructure. I've also worked on transport and systems for the past 20 plus years. I've worked on the quick specifications at the IETF and various other things. I've spent my spent time at Google, and before that, I was in academia for quite a while. So, getting to the meat of the talk here, I first want to set expectations that we've had our fair share of outages, as have many of you in this room. However, we are not here to do a postmortem of these talks because this is not the right place for us to do a detailed postmortem of a lot of them. However, the themes that we want to discuss today are those that might be familiar to you, and that's much of the goal of this talk is to talk about the themes that we have learned by doing through these investigations. And we are going to say some themes that might be familiar because they are worth repeating. And sometimes repetition is the way that we get ourselves to really appreciate the value of something. And if you have not seen this before, then it's worth your time. You have about 20 minutes to the end of this talk to go buy, order a copy of this book. Please get this book. It is one of the most important books that anybody who builds software or systems or deploys any of these things should have on their bookshelf. So let me start by just giving you a brief sort of a breakdown. We've tried to do like a classes of root cause thing here, and the kinds of things that we experience, we try to break them down into easy to detect and hard to detect root causes. With There are things that are easy to detect, and these are things that are typically triggered by explicit failures of other things, such as hardware or network failures. When you see a hardware piece of hardware failing, or when you see a component of the system failing very explicitly, and when you see an operator having an outage, that's very easily visible. Similarly, there are change induced outages. When you deploy a change across the fleet, you are able to catch that and you are able to see that it's happening along with the change. Similarly, there are load related changes where there's load in the system that changes because a customer puts enormous load on the system, or there's an expected increase in load on the system, and that can cause outages or issues. And those are typically easy to detect because those events are known and they're happening, or there are other signals that very clearly tell you that there is an event that's happening. There are harder to detect issues such as dormant code paths, for example. Now, these are code paths that are typically not triggered uh, by during normal execution, or they haven't been triggered for a long time. And after a period of time, or something shifts, something happens, an input changes, or a customer config changes, and that causes a particular piece of code to get triggered. Now, you might be looking at this and going, well, we've been doing fuzzing for a long time, and that's true. However, in a complex system, in a complex piece of infrastructure where you have a lot of interacting components, it's much, much harder to do fuzzing of the entire system. And so you still have these dormant code paths through the system that can get triggered, sometimes arbitrarily by a customer config change at an arbitrary time of day when you have no idea what's happening. Then there are interacting bugs where individual bugs don't have the kind of signal that to surface to become visible, but then multiple such bugs can come together to cause a large signal that is greater than the sum of its parts. And then there are hidden bottlenecks. Now, these are limits in the system which you don't encounter or you don't realize exist until you hit the limit. And that can happen in a variety of ways, but usually it surfaces as a failure somewhere downstream. So somewhere something downstream is failing, and then you have to work backwards to see what is causing that failure, and you realize that it's a bottleneck somewhere else in the system that's causing that to happen. So these are these are different kinds of root causes that we encounter in our debugging and in our system, in our issues and outages. The talk isn't exactly about these. The talk is a little bit more around themes that we want to cover. You'll see some of these things I just discussed show up. But the themes we want to cover are divide and conquer, keeping an audit trail, and why resolution matters. So those are the themes that we are going to try and cover in this talk today. So let me start off with divide and conquer. Divide and conquer is the idea that you want to be able to isolate an issue by going towards progressively smaller, by basically dividing this problem space, and you go closer and closer until you isolate the problem itself. So with divide and conquer, we have an example for where for instance you can see signatures which allow you to easily isolate the problem. So here's a graph. The x-axis is time and the y-axis is the number of hosts carrying a particular kernel version. You get some brownie points for finding Batman in this picture, but these shapes are very specific. These are specific because we roll them out in quadrants, and you're seeing the roll happening in quadrants. We do fairly rapid kernel rolls at Fastly, and we have a high velocity release cadence, but the cadence of release is there, and there's also shape to the way the release itself happens. This gives you a baseline. You get an organic timeline to observe issues that pop up. So when an issue pops up and it's lined up with this particular shape, it becomes very clear that it has something to do with the kernel rolling out. If the release cadence doesn't line up with the issue that you're looking at, we can use another strategy. And this other strategy is available to you if you have a large infrastructure. Because if you have a large infrastructure, you can do multiple parallel experiments across the fleet to try and divide and conquer. Let me give you an example. So here's an example of a recent issue where we had a regression, and with the regression, we couldn't really pinpoint it to something. So what we had to do here was to try multiple experiments. And as you can see here, up until a certain point, all the experiments are following the same curve. And at a certain point, you start to see divergence happen. Specifically, if you're able to see the color here, it's experiment 1 is in blue, experiment 2 is in brown, but experiment 1 and 2 sort of diverge from the baseline. And now this is basically showing you that experiment 1 and experiment 2 both diverge. Experiment 2 happened to be a later version of the same piece of software here that we were trying experiments with. So experiment 1 was really the piece of software that contained the change that caused that regression behavior. So we were able to use multiple parallel experiments to divide and conquer here. I will note, however, that this relies on a departure from the baseline, and that can be tricky. You can have a situation where the baseline itself is not a great baseline. So I'll give you this example, and I'll tell you what I mean here. So here's again time on the x-axis, and on what you're seeing here is whatever metric we were tracking here, and you're seeing version 98 of the software, version 100 of the software, and something that happened. So we notice a regression when we went from 98 to 100. And you can see that increase in the value, which is a bad thing for this metric. And we found that there was a regression. We started to dig into it. We dug into it, found the issue, and we fixed the issue. And when we fixed the issue, the fix actually resulted in the metric going much further below what the baseline used to be before we got to 100. What this revealed to us, and much digging later, what we realized is that there was a regression in the software a couple of years ago, and that there was human failure at the time that caused us to miss that regression, and we accepted this new number as the baseline. So when we regressed from the baseline had already regressed from the past. And so when we fixed the issue, we actually fixed the earlier regression as well. This is an important thing because it tells you that simply saying regression from the baseline is not adequate, because sometimes your baseline itself is not adequate. Now, I've seen this several times. When we set a baseline for performance of something, we often use current behavior. New congestion controller, if you want to deploy that, for instance, you look at the existing behavior of existing congestion controllers and you look at that to go, okay, well, that's the baseline, and we're going to use that to measure the behavior of everything else. What this says is that the ground truth could be somewhere else. And that's something also to be mindful of. When you're setting your baseline might already have regressed from what you truly could be. So just something to bear in mind. One more note here, that as you're doing these experiments, an important thing to note is that even though I said earlier that you can look at signatures of things rolling out and so on and so forth to see if that could be the cause of a change. Here's an example to prove exactly that that could be not necessarily the case. We saw a regression in latency metric. There was a new feature rolling out. And long story short, we thought that this might be the reason why the regression was happening, but it was not the case. Now, there are guaranteed, if you're a large enough system, you're guaranteed to have multiple changes going on. You will routinely find correlation, and there will be many red herrings. And we had to work through and rule out this particular feature, which correlated with this metric regression. And everyone was convinced that it was the root cause until we turned it off and realized that it was not. It didn't change the metric. That's a bit about divide and conquer. And at this point, I'm going to hand it off to Hossein to carry on.
Thanks, Jana. Hi, everyone. I'm Hossein. I am VP of Engineering and Network Systems at Fastly, and excited to be here to talk about some of the lessons that we've learned. My group is responsible for building efficient, cost-effective, and scalable systems that connects Fastly services to end users and customers' infrastructure. Some of the functions of my group are kernel, hardware engineering, network architecture, network modeling and configuration, traffic engineering, data path, and layer 7 load balancing. I've been building networks for 20 plus years, and it seems like there's a trend of ever-increasing complexity, scale, and efficiency over time. And prior to Fastly, I have hyperscale environment experience at Google. I also had a startup focused on network testing and modeling. All right, so let's dive in. Jana talked about some of the themes. One of the themes that we saw that can help with these long-running investigations and things to keep an eye on. I want to talk about keeping an audit trail. This is something that all large-scale operators are used to and is part of their practice, but I do want to highlight a few things more. First, this is actually one of the things that if you get that book or if you read it, you'll see that this is a very interesting story about nuclear submarines and how the operators are trained to respond to incidents. Apparently, there is a brass bar on top of the control panel. And the instruction is, if you see an alarm going off, you have to touch the brass bar with both hands and observe the panel. The idea is that they want to essentially prevent the operator from making an immediate adjustment in response to an alarm without fully surveying all of the signals in front of them and making an informed decision. So same thing that goes to large-scale infrastructure. Even if the issue seems familiar, don't act on a subset of the signals. Make sure that the operators look at all of the signals and then make changes as necessary. Now, if we talk about how to respond to the incidents, a lot of times, as Jana was saying, we can find a very clean correlating signal that maybe it was a bad change that needs to be rolled back. So the response to that is simple. We use the existing release mechanisms that we have to be able to change things in the production network. But then there are oftentimes things that you need to go off script, things that essentially a live change of the system is required, or you want to actually do multiple experiments to be able to divide and conquer and find what the issue is. In those cases, you need to break the glass. And breaking the glass, again, we're really good at keeping an audit trail generally in large-scale environments when we're releasing software. That's common in our industry these days. But then when you break the glass, we deviate from standard operating procedures. And these are necessary times where you need to inform all the responders about what you're doing. And the incident commander has to make sure that everyone is informed of all of these experiments going on. We've been bitten by this a few times. This is an example of an investigation where someone was making a change to production, essentially creating an A/B condition to observe which one of the changes essentially favorably changes the shape of the graph and resolves the issue. Another responder wasn't aware of this, and they got confused about this banding that has happened, which was natural for that experimentation. And, a few minutes of time was lost during a call as the second responder was trying to figure out why this banding exists. So again, it highlights the importance of incident commanders essentially keeping everyone in the loop when we had to break the glass and we're running these experiments. The third theme that I want to bring up is about resolution and resolution in the telemetry signals that you collect. Let me use this example In general, if you look at these dominoes that are placed in a circle pattern, if you see the dominoes in 1 second being all untouched, and then the next second you see them being scattered, you can't really tell which was the first domino that fell. And in a lot of times, not being able to say which one was the cause and which one was the effect will lead into different hypotheses and different theories. It's extremely important. If you imagine that in this scenario, you can actually have a high resolution camera that can tell you exactly in time what was the first domino that got dropped. So let me take you to an example that happened in our network. This is an incident that we're responding to. It was one of the longest running investigations that we had at Fastly. Generally, the mindset here is that we quickly want to stabilize the production network to the point that there's no customer impact. But then once we do that, the rest of the investigation about the root cause and how to essentially prevent it from happening against. So all of the stuff you're seeing here is that post-acute response. But it's very important for us to understand how things happen and why they happen so we can prevent them from happening again. In this scenario, the two metrics that I'm presenting here, which actually are coming from that specific incident, are very confusing because they happen exactly at the same time step. And depending on which one is the cause and which one is the effect, it leads to completely different explanations. One of them means, some part of the stack is misbehaving and another one is another part. So going back to that domino example, let's take a high precision camera and actually see if we can capture in time which domino was the first one that was dropped. In our scenario, what we ended up was that we changed a whole lot of things in our observability pipeline in order to be able to capture the things at the 1 second resolution, and not in some cases sub-second resolution. And you can see the impact, you can see the signal and the way that it was collecting, and then being collected, and you can see the impact of 1 second intervals when we introduced them. And sure enough, after that, we were able to cleanly see a correlation there. We saw the first domino that was dropped. And it helps us to see that here's cause, here's the effect. You can actually sort of see the onset of the issue on the top graph. The second one was just simply an effect. And after that, actually finding the root cause was fairly quick. My takeaway here is that build the ability to be able to crank up the resolution and sampling frequency in your observability pipelines. It's not something that is feasible or cost effective to do it at scale at all times. But once we have that capability, then we can build a whole lot of automated triggers that the system senses that something is brewing. And it can actually automatically engage that high sampling mode when it senses the signs of the trouble. And that's something that we've learned and implemented in our systems after that incident. The other thing that we observe doing these investigations is that a lot of times people want to introduce a new metric to be able to see things more clearly or validate the hypotheses. But the problem is, if you haven't seen the shape of the new metric in steady state, it's extremely confusing to see it during the middle of an incident. I'll give you one example again from real life. We introduced the top right metric during an incident, and there were those little spikes. And sure enough, the team focused on those spikes, trying to come up with a hypothesis why they're happening, what do they mean. And it took them on a completely different tangent. It turns out that those spikes are absolutely normal. It's the behavior of the system and had nothing to do with the incident. So generally, I highly encourage that all of these signals, all of the things that you think are useful for during an investigation, to collect them ahead of time and train the eyes of the responders to what the steady state signal for these metrics look like. I know it's easier said than done because a lot of times we don't know what we don't know. But if you're forced to introduce the new KPI and new telemetry signal during an investigation, at least take it with a grain of salt because we don't know what the baseline looks like. And another things that we commonly say here at Fastly is if you didn't fix it, it ain't fixed. A lot of times the underlying root cause goes away. Going back to the class of issues that Jana was saying, sometimes it's a compounding effect based on a code path that is rarely exercised or a customer pattern of interesting traffic. that is put on our network. And if you take one of those elements away, then the issue appears to be gone. But until we identify what the root cause was and make sure it's not happening again, it's not fixed. And that's something, again, that's why we have this acute response, but we don't close out these incidents until we get to a point where we can confidently say that we've identified the root cause and it's not going to happen again. All right, that was my last slide. Thanks for your attention.